All right, so next up is directing groups. So not only do substituents activate or deactivate a ring, they also affect the position of future substituents. So for example, if you have your benzene ring and it's got some kind of substituent, which we'll just call A, and then you wanted to add some kind of electrophile, we'll call that just B plus. You can have up to 3 options of where you're going to add it, right? You can either add it right next to your current group. This is what's known as the ortho position or the 1-2 position. You can add it in the meta position. Or the 1-3 position. Or finally, you can add it to the para position or the 1-4 position, right? So there's 3 different places that you can add it to, and where it gets added depends on what kind of group it is. So all activating groups will lean towards ortho or para directors. With para in general being preferred because the ortho position is more sterically hindered. So if we think about why are they ortho para directors, it all has to do with resonance structures. So if we take a donating group like an alcohol, right, we can draw a whole bunch of resonance structures. So we can kick this lone pair down to here and then move this pi bond onto this ortho position. Then we can take this lone pair, make it a pi bond here, and then move it onto the para position. And then, of course, we can add it to the ortho position on the other side of the ring. And then, of course, we can go back to our original structure. But what you can see is that the resonance structures, not only do they donate electron density into the ring, they donate it into the ortho and the para position. So when we're thinking about this ring, what we want to recognize is that the ortho and the para positions actually have a partially negative charge. And that's part of the reason why they're ortho para directors. The real reason has to do with the intermediate. It stabilizes the intermediate. So it stabilizes the ortho / the para positions. Let's go take a look how it does that. So we have our phenol with our electrophile, right? So it could donate this into here, and then we could have this pi bond attack our electrophile. Right, so there's one option. On the other side, we could have it attach at the para position. And again, what we can do is we can draw these electrons coming from the oxygen. So we can kick those down here, take this lone pair over here, and then have that attack the electrophile. If we try to do the same thing with the meta position, what we'll notice is that we can't make the electrons come from the oxygen. It has to just come from the benzene ring. And so what your structure ends up looking like is this, right? There's no way we can get this lone pair down into this position over here. And if we think about these three structures, the one in the middle is the worst structure because it has an unfilled octet. The structure on the left and the right have filled octets. Remember, that's the most important thing for a good resonance structure. A good resonance structure has filled octet.